Have you ever pondered why some materials conduct electricity while others don't? This question has perhaps puzzled many of us at some point, and it's worth the time to explore it further. You might have noticed how metals like iron, copper, and aluminum conduct electricity effortlessly, while materials such as rubber, glass, or wood fail to do so. This variance in electrical conductivity isn't a mere coincidence. It is the manifestation of a fascinating principle referred to as the energy band theory. The energy band theory, for those unfamiliar, is a fundamental concept in solid-state physics, and it could be the cornerstone of understanding electrical conductivity in different materials. It's a theory that provides us with profound insights into the behavior of electrons within solid structures. It helps us see beyond the surface to comprehend the interactions happening on a microscopic level. Picture this. In an isolated atom, electrons move in well-defined energy levels, often visualized as orbits. But what happens when multiple atoms come together to form a solid structure? That's where things get intriguing. As these atoms bind together, their individual electron energy levels start to merge, overlap, and interact with one another. This merging process results in the formation of numerous closely packed energy levels, which are collectively referred to as energy bands. These bands signify the range of energy that an electron may possess within a solid substance. When these energy bands are populated by electrons, the bands either become completely filled or filled. The nature of these energy bands, particularly the filled and unfilled bands, plays a crucial role in determining whether a material will conduct electricity or not. It's an intricate dance of atomic interaction, an electrifying ballet that goes unnoticed to the naked eye, but crucial for the functionality of our electronic devices. Stick around as we embark on this journey to unravel these fascinating phenomena. First off, let's delve into the energy band theory. It's a concept that helps us understand the behavior of electrons in solids. Essentially, when multiple atoms come together to form a solid, their energy orbits overlap, creating what we call energy bands. Now imagine these bands as a set of shelves. In this visual representation, the various shelves carry different levels of energy, each serving its own unique function. On these energy shelves, you'll find that certain areas are teeming with activity, while others remain relatively unoccupied. The shelf closest to the ground is what we commonly refer to as the valence band. Picture this as the lowermost shelf of a bookcase, where electrons reside when the temperature is brought down to absolute zero. These electrons are generally stationary, content in their place. They resemble a group of individuals who have settled down, neither too excited nor too agitated. Their state of calmness suggests that these electrons don't actively participate in conduction, rather they prefer to stay put, maintaining the status quo. In contrast, the upper shelf portrays a markedly different scene. This level we call the conduction band. Akin to a playground teeming with children, this band is a hub of activity. Here, the electrons are free to move, to jump from one spot to another. It's like they are given the ticket to freedom, enabling them to the flow of current. This kinetic energy that they possess is what we refer to as conduction. However, it's not all as simple as it sounds. There's a twist in the tale. Between the valence band, the calm and composed lower shelf, and the bustling conduction band, the energetic upper shelf, there exists a gap. This gap is known as the forbidden gap, a term that implies an element of mystery and intrigue. It's neither a part of the lower shelf nor the upper one. This gap acts as a barrier, an obstacle, a hurdle, preventing electrons from the valence band from easily moving to the conduction band. The existence of this gap reminds us of the complexities of the world of electrons. It's akin to a river that separates two lands, a wall that divides two territories. The size of this gap, the width of this river, or the height of this wall plays a crucial role. It can determine whether a solid is a conductor, an insulator, or a semiconductor. It's this forbidden gap that stands as the gatekeeper, the decision maker of the world of electron flow. So, how does this classification work? Let's begin by understanding how materials, specifically conductors, insulators, and semiconductors, influence the behavior of electrons, and consequently, the flow of electricity. Conductors, as the name suggests, are materials that easily allow the passage of electrical current. Their unique characteristic lies in the fact that their valence and conduction bands overlap. So, what does this mean for the electrons within these materials? This means that the electrons, which are negatively charged particles, can move freely between these bands. This freedom of movement of electrons is what allows the smooth and seamless flow of electrical current through these materials. Copper and silver are quintessential examples of conductors that are commonly used specifically because of their high conductivity. Now, on the contrary, we have insulators. Insulators are materials that resist the flow of electricity. Unlike conductors, insulators have a broad forbidden gap. This gap presents a considerable challenge to the valence electrons, as they are tightly bound and cannot cross this gap to reach the conduction band. Essentially, this vast gap acts as a barrier, preventing the free flow of electrons, and thereby making insulators like rubber or glass poor conductors of electricity. There's another intriguing category of materials that exists: the semiconductors. Semiconductors exhibit properties that place them somewhere in the middle of conductors and insulators. Unlike insulators, they have a relatively smaller forbidden gap. This implies that under specific conditions, or with the right amount of energy, electrons can take the leap from the valence band to the conduction band. It's this unique feature that lends semiconductors their versatility. Semiconductors like silicon and germanium have been integral to the development of cutting-edge technology. They are at the heart of electronic devices, right from your everyday gadgets like smartphones and laptops to high-end technologies like satellites and space probes. This unique feature makes semiconductors like silicon and germanium integral to electronic devices. To sum up, the electrical properties of solids hinge on the energy band structure and the size of the forbidden gap. This fundamental principle is central to our understanding of the behavior of matter at the atomic level. The nature of these bands, as we have seen, can be quite complex, but they ultimately determine the conductive behavior of a solid material. In more detail, these bands represent different energy levels that electrons can occupy within a solid. The band structure is a representation of these energy levels, and the forbidden gap signifies an energy range where no electron states exist. The size of this gap is a key distinguishing factor between conductors, semiconductors, and insulators. When we talk about conductors, we are referring to materials such as copper or aluminium. These materials have overlapping valence and conduction bands, which means electrons can easily move from the valence band to the conduction band. This is what allows electric currents to flow easily, making conductors essential for constructing wires and other components in electrical circuits. On the other hand, insulators like rubber or glass possess a large forbidden gap. The electrons in these materials have a hard time getting enough energy to jump from the valence band to the conduction band. This lack of free movement is what inhibits the flow of current, making insulators an ideal choice for protecting us from electric shocks. Semiconductors, like silicon and germanium, occupy a unique middle ground. Their forbidden gap is small enough to allow some electron movement, but not as freely as in conductors. This special characteristic lets semiconductors act as both conductors and insulators under different conditions. Their behavior can be controlled, making them invaluable in the creation of electronic components such as diodes, transistors, and even the microprocessors in computers. Remember, understanding these principles is not just academic. These concepts are at work every day in our lives. When you flip a switch to illuminate a room, or when you swipe your finger across your smartphone screen, you are interacting with the practical applications of these principles. So the next time you switch on a light or use your smartphone, remember, it's all about the bands. The energy bands, that is. Scene script, voiceover. Now let's delve deeper into the energy band gap of two common semiconductors, silicon and germanium. These two elements are fundamental in the world of electronics, and it's their energy band gaps that make them so useful. First, let's talk about silicon. Silicon has a small energy band gap of 1.1 electron volts at room temperature. This small gap allows for controlled electron movement, making silicon the ideal material for most electronic devices. Its ability to control electron movement means it can be used to precisely control electrical current, which is why it's so widely used in computer processors and other digital circuits. Next, let's talk about germanium. Germanium has a slightly larger energy band gap of 0.66 electron volts at room temperature. This makes germanium less efficient than silicon at controlling electron movement, but it's still useful in certain applications. Germanium was actually the material used in the first transistors, but was quickly replaced by silicon once its superior properties were discovered. Understanding these energy band gaps is crucial in the world of electronics. The specific properties of silicon and germanium, dictated by their energy band gaps, allow us to build the incredible range of electronic devices we rely on every day. From your smartphone to your laptop, it's all about the energy band gap.